hear me? Do you hear me?
Yes, sir.
And the screen is also visible?
Yes, sir.
So let us continue with the main goal, namely fundamental theorem of calculus in the Lebesgue integration technique, in the theory of Lebesgue integration. Okay. So how do we generalize fundamental theorem of calculus available in Riemann integration theory to the setting of Lebesgue integration? That's the main goal. And we were collecting certain background material to prepare ourselves to this main goal. And to this end, I have introduced a new class of functions called functions of bounded variation. Okay. Let me quickly recall the definition to begin with. Let us assume that we are given with a function on a closed bounded interval AB, real or complex valued. As in the Riemann integration theory, let us fix a partition P of AB. As you know, a partition demands that x naught is the left extreme point of the interval. Further, x1, x2, x3, etc., xn are strictly increasing and xn coincide with right extreme point of the interval. You consider a typical subinterval introduced by this partition. Let us say xi minus 1, xi, the ith subinterval, and consider the variation of f on that subinterval. That is, look at f of xi minus f of xi minus 1 in the absolute value. And do it for each partition subinterval determined by the partition and sum it. This quantity we shall denote by, I hope this is the notation I used, variation over AB of the function f corresponding to the partition P. V, A, B, P, F. Now you can vary the partition and look at variation of the function over different partition and look at the supremum of all such variation. Look at supremum of variation over AB corresponding to the partition P of the function f, where supremum is taken over all the partition. And this quantity we shall denote by variation of f over the interval AB. This is the definition of variation. It should be clear from the definition itself that the variation VABF is non-negative. It could be plus infinity. We don't know whether VABPF as a set is bounded or not. Therefore, the supremum could be plus infinity. In case it is finite, if the total variation of F over AB is finite, then we declare that F is of bounded variation. That's the definition. To put in simple terms, a function is of bounded variation over AB if the total variation is finite. And we have seen certain properties of functions of total variation. For instance, bounded variation. For instance, we have seen that a function of bounded variation is necessarily bounded. Okay. Let us continue to collect a few more basic facts about functions of bounded variation. So some more facts. We are doing all these things to prepare ourselves for fundamental theorem of calculus in the Lebesgue integration theory. Let us consider a function, let f from AB to R, or to be more general, AB to K, where K is R or C, P of bounded variation. Let us look at points, arbitrary but fixed for the time being, namely x and y. For x comma y in the interval AB with x less than or equal to y as indicated in the picture, let us look at variation of f not on the whole interval AB but on the interval xy, closed interval xy. For x comma y with x less than or equal to y, let Vxyf denote the variation of f on the interval xy. In the interval closed interval xy, assuming x is strictly less than y, and in case x equal to y, I shall denote or define this quantity to be 0. And let us define Vxyf is equal to 0 if x is equal to 1. Then the fact that I want to bring to your notice is the following. The total variation of f over the interval AC plus total variation of f over the interval CB is equal to total variation of f over the interval AB, where C is any point between A and B. Essentially, this equation tells you that variation of f over an interval AB is additive over subintervals. So this is what we want to establish first. That's not hard. So in order to talk about variation, total variation, you need to talk about variation over a partition. So let us start with a partition. Okay. Let P be a partition of AB. Let us say P equal to x0, x1, x2, and so on, xn. We want to establish this fact, namely the total variation of f over an interval is additive. So let us take this partition AB. A is obviously x0 as per the definition of the partition. This is xn, and you have intermediate point. Okay. Please note that the point C, which you are picking between A and B, may or may not be a point in this partition. May or may not be a partition point. Okay. So what I do is, in case it is not a partition point, let us introduce that. Okay. So let us introduce C. The partition P, let me note down those things. May or may not contain the point C. Okay. Let us introduce C in, to be precise, xi minus 1 xi. Okay. In case C is not there, I shall introduce C in the ith subinterval. Now please note that the partition P along with the introduced point C gives a partition of AC as well as CB. Do you agree?
Yes, sir.
So let me call the partition of AC given by P as P1 and partition of CB given by P as P2. Okay. Then P provides a partition P1 of AC and P2 of CB. Somehow we want to relate the total variation over AC, CB with the total variation over AB. And for relating total variation, I first find how the variation with respect to partitions are related. Okay. P2 of CB. To put in simple language, P can be thought of as P1 union P2. Okay. Now let me consider the variation of F corresponding to the chosen partition P over the interval AB. Okay. By definition, this is, look at the partition and find the variation over each subinterval and sum it. Okay. So that will be summation I is equal to 1 to n modulus of f of xi minus f of xi minus 1. Let me split this summation into, I want to segregate this xi minus 1 xi interval with the other things. Okay. So let me split this into summation k is equal to 1 to I minus 1 modulus of f of xk minus f of xk minus 1 plus the ith term f of xi minus f of xi minus 1 plus summation k equal to I plus 1 to n modulus of f of xk minus f of xk minus 1. Simple algebra. Now what I do is, in the middle term, I will introduce f of c. This is less than or equal to summation k is equal to 1 to I minus 1 modulus of f of xk minus f of xk minus 1 plus, now in the middle term, introduce f of c and apply the triangle inequality. Modulus of f of c minus f of xi minus 1 plus modulus of f of xi minus f of c plus summation k is equal to the third term, third summand, I plus 1 to n modulus of f of xk minus f of xk minus 1. Do you agree?
Yes, sir.
Yes, sir.
Now first two terms, that is summation k equal to 1 to I minus 1 modulus of f of xk minus f of xk minus 1 plus f of c minus f of xi minus 1. Can you tell me what it is? Look at the picture.
Partition of AC.
It's not partition, it is the variation, right?
Yes, sir.
It's the variation of f over the interval AC corresponding to the partition P1. Okay, so that is equal to variation over AC corresponding to P1. Function is same. F. Similarly, third and fourth term summed up will give you variation of F over the partition P2 corresponding to partition P2 over the interval CB. Okay. But variation corresponding to a particular partition is less than or equal to total variation. So this is less than or equal to total variation of F over the interval AC plus total variation of F over the interval CB. So far so good. And look at the right hand side. Right hand side is total variation, not total variation, variation of F corresponding to an arbitrary partition. Okay. Since variation of F over AB corresponding to an arbitrary partition P is less than or equal to this, total variation also will be less than or equal to this. Okay. Hence, total variation of F over the interval AB is less than or equal to total variation of F over AC plus total variation of F over the interval CB, giving you inequality. We want to prove the equation. So other way inequality we have to demonstrate. So this, let me put *1. Now for the other way inequality, I shall use the definition of total variation. Keep in mind that total variation is essentially a supremum. So least upper bound. Therefore, nothing lower than it can be an upper bound. So I'm going to make use of those facts. Okay. So let epsilon be greater than 0. Okay. Select a partition P1. This P1 has no connection with the P1 that I have used to get *1. Select a partition P1 of AC and P2 of, let us say, the interval CB such that, yes, now I am going to use definition of supremum. Total variation over AC of F minus epsilon by 2 cannot be a upper bound, is less than or equal to total variation over AC corresponding to the partition P1F. Such a partition P1 exists. Similarly, VCBF minus epsilon by 2 is less than or equal to variation of F over the interval CB corresponding to partition P2. Do you agree with this?
Yes, sir.
Simply the definition of supranorm. Okay. That implies now you add VACF plus VCBF minus epsilon is less than or equal to VACP1F plus VCBP2F. Okay. Variation of F over AC and CB corresponding to partition P1 and P2. Okay. Now you can realize that these partition P1 and P2 put together will give you what? P1 is a partition of AC and P2 is a partition of CB. Okay. If I put them together, what I will get?
Partition of AB.
Partition of AB, and that will be that put together can be symbolically represented as P1 union P2, right? Okay. Note that P1 and P2 put together gives a partition P of AB. So the right hand side can be identified to be total variation of F over the interval AB corresponding to the partition P1 union P2. Do you agree? Do you agree?
Yes.
Now, this total
Yes, sir.
variation, corresponding to a particular partition, namely P1 union P2, not total variation, variation corresponding to a particular partition is less than or equal to total variation. So this is less than or equal to total variation of F over the interval AB. Thus, what we get is variation over ACF plus variation, look at the right hand side, of F, total variation of F over the interval CB is less than or equal to total variation of F over the interval AB plus epsilon. Epsilon I am transposing to the other side. Now epsilon is arbitrary. Since epsilon greater than 0 is arbitrary, we infer that total variation of F over the interval AC plus total variation of F over the interval CB is less than or equal to total variation of F over the whole interval AB. Now this is star 2, and now you club star 1 and star 2, you will get the desired result that total variation over the entire interval can be split into 2, or total variation is an additive, has an additive property. Okay, so this is first fact that I would like to record. Now next fact is the following. I did not number, so let us put this as 1, then 1. Okay, the second one is this. V total variation of F over the interval AX. Given interval is AB. Now I am fixing X between A and B. For X in AB is an increasing function. Is an increasing function as a function of x. As x increases, the variation of f over the interval ax also increases. That's easy to see. So you are given with the master interval AB. I am picking 2 points x and y with x less than y. Okay, that x is less than y. I have to prove that variation over ax is less than or equal to variation over ay. Okay, so first I will take a partition of ax. Consider a partition P of ax. Okay, and now let me consider P1 equal to that P union Y. Then I will get a partition of AY. Gives a partition of the interval A comma Y. Okay. Now, variation of F over the interval AX is less than or equal to variation corresponding to partition P. Okay, corresponding to partition P is less than or equal to variation of F corresponding to partition P over AX plus I am adding a non-negative term. And what is that term? Mod Fy minus Fx. This is being added. Okay. And can you identify what is the quantity in the right hand side? You have Ax and you have a Y. Yeah. Can you identify what is appearing in the right hand side? Yes or no?
Variation of AY.
Variation of
Variation of function f corresponding to partition P1 over AY. Is that okay?
Yes, sir.
And that is less than or equal to total variation of f over the interval AY. So look at the left hand side. We have started with an arbitrary partition and variation of f corresponding to partition P over AX is less than or equal to variation of f over AY. Okay, and this is true for each partition. Hence, supremum VAXF is less than or equal to VAYF. And this tells you that VAX of f as a function of x is an increasing function, monotonically increasing function. Okay. In fact, you can see this in another way by using the previous fact number 1. Please note that V total variation of f over the interval AY is equal to total variation of f over the interval AX plus total variation of f over the interval XY. This is because of fact 1. Yes or no? The total variation is additive. So by fact 1, we have this. And this one is greater than or equal to total variation of f over AX because each of those quantity appearing in the right hand side is non-negative. Okay, and this proves. But I went for a different proof because this will be used again later. Okay, that proof will be used. So in any case, the total variation over AX as a function of x is an increasing function. Okay. Now, next fact I want is the following. You are given with a function f from AB to k, and you are looking at variation of f over the interval AX. now, modulus of fy minus fx for the given function is less than or equal to variation of f over ay over the interval ay minus total variation of f over the interval ax for every a less than or equal to x less than or equal to y less than or equal to b. You are given with ab. I am picking two arbitrary but fixed for the time being points x and y, x less than or equal to y. Then I have this relation. Okay, the variation of f in the interval xy, namely mod fy minus fx is less than or equal to this quantity. That's not hard to see. Again, let us write a quick proof of this. We have fy minus fx is less than or equal to mod fy minus fx. Okay. Now look at the proof of second fact that I have written here. I have written that variation of f over the interval over the partition p over the interval ax is less than or equal to this. Okay, so from that inequality, you should be able to see that mod fy minus fx is greater than or equal to Vax pf here, and that is equal to Va. So from this, so let me just mark it here. 1 minute. So look at this. I will call it as star star. Okay, and looking at it, I can write the following inequality. This is less than or equal to Vayf minus Vaxf. Okay, C star star. This is the reason why I went for a different proof for the fact. Now use that star star carefully. You can observe and you can write this. Let me not spend more time on it. Therefore, what I have is, yes, that's what we have to prove. Mod fy minus fx is less than or equal to. So we are done with. Now let us proceed with the next fact. The next fact is the following. Vayf minus fy is greater than or equal to Vaxf minus fx. That is again a rewriting of the third one, possibly. Okay. Say, look at this. Fy minus fx is less than or equal to Vayf minus Vaxf you have. So now transpose suitably, you will get this. Okay. So what I will write, this is star 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 from star star star. Is that okay? Yes or no?
Yes, sir.
Now what
Yes,
this inequality tells you? What this inequality tells you? Vayf minus f of y is greater than or equal to Vaxf minus f of x. Remember, x and y are like this. X and y are 2 points between a and b, and x is less than or equal to y. So what does this inequality tells you? You look at a function Vaxf minus fx, call it as g of x. Then what it tells about g of x? Is the question clear? I am asking you to look at this. G at x is equal to variation of f over the interval ax minus fx. Now this is a function of x, and the previous inequality tells you something about this function. What is that? Does it tell you that G is increasing?
Yes, sir.
Then G is an increasing function. By increasing, I mean non-decreasing, monotonically increasing function. On AB. Due to, how does it come? How you can infer that it is monotonically increasing? Due to fact 4, previous fact. Okay. So we have observed a few things about total variation of F over the interval A to some arbitrary point X. 4 facts we have observed. Okay. Now we have following theorem, which is quite easy to prove, but it's an important theorem by Jordan. Okay. The theorem characterizes the bounded variation function. It gives you a necessary and sufficient condition for a function to be of bounded variation. Let f be a function from AB to K, then f is of bounded variation. I hope I have introduced the notation for collection of all bounded variation. That is, f belong to BVAB. BVAB is the vector space of all bounded variation function defined on AB. Okay. Then f is of bounded variation if and only if and only if f can be written as f is a difference of two monotonically increasing function. This is an important characterization of functions of bounded variation. Okay. It precisely tells you when a function will be of bounded variation. That can happen if and only if that function can be splitted into two functions, difference of two functions, both of which are monotonically increasing. Okay. One part is obvious proof. This part. Namely, suppose f is the difference of two monotonically increasing function. Then it is easy to see that f is of bounded variation. Can somebody tell me how does it follow? Suppose f equal to g1 minus g2, where g1 comma g2 are monotonically increasing. Then I have to claim that f is of bounded variation. It is quite obvious. Please remember the first class of functions that I gave you as examples of bounded variation function. After defining bounded variation function, I gave you as an example, this class of functions will be definitely of bounded variation. Which is that class? Can somebody remind me?
Monotonic function.
Monotonic functions are of bounded variation. Therefore, if G1 and G2 are monotonic, increasing, definitely they are of bounded variation. So G1 and G2 are bounded variation. Next, we have seen class of bounded variation functions are well behaved. Their sum, their scalar multiple, etc. are of bounded variation. Therefore, if G1 and G2 are monotonically increasing, G1 and G2 are bounded variation, and hence G1 minus G2 is of bounded variation. Okay. In particular, G1 comma G2 are of bounded variation. I will just write PV, and hence f equal to g1 minus g2 is of bounded variation. So this finishes one part. Now the converse. That is, if f is of bounded variation, I have to split it into difference of two monotonically increasing function. Conversely, that also we have done already. We have to just assemble the things. Conversely, let f be of bounded variation. I have to write f as difference of two monotonically increasing function. Let g of x is equal to variation of f over the interval ax, and h of x is equal to variation of f over the interval ax minus fx. You have seen in fact 1, 2, 3, 4. 4 facts I have written there. Out of that 4, 2 says that both G and H are monotonically increasing. Yes or no?
Yes, sir.
Then G comma H are monotonically increasing. That we have established in facts numbered from 1 to 4. Now you just see the difference of G minus H. Further, G minus H is equal to f of x. F. Okay. Therefore, f you could write as difference of two monotonically increasing function. So this is an important theorem about the bounded variation function. A function is of bounded variation if and only if you can write it as difference of two monotonic functions. Okay. So I will stop the discussion of bounded variation function here. But remember, our aim is to collect materials needed for proving fundamental theorem of calculus in the Lebesgue theory, Lebesgue setting. Okay, so bounded variation I will stop here. Now let me just state a result which we may use to prove fundamental theorem of calculus. Okay. Next, background material needed. I am not going to prove that result. I will just state that result. But to motivate that result, from basic real analysis, I think you know something about continuity of monotonic function. Can somebody remind me? Suppose you have a monotonic function, increasing or decreasing, over an interval AB. What can you say about its continuity? Or to be more precise, what can you say about points of discontinuity? How many may be there? I am talking about the cardinality.
At most countable.
At most countable. So a monotonic function over an interval may be discontinuous, but it has at the most countable number of discontinuity. Now you know Lebesgue theory, Lebesgue measure, etc. And you know the meaning of almost everywhere. So can I state the same result as a monotonic function is continuous almost everywhere?
Yes, sir.
Because discontinuity is of countable and measure of countable set is 0, right? So let me write in that manner. Recall from basic analysis that a monotonic function f from AB to R is of, sorry, is continuous almost everywhere. is continuous almost everywhere. This may not be the language you use there, but you can put it in this language. Continuous almost everywhere on AB. The next theorem I was talking about, which I will state but not prove, is a far-reaching extension of this result. This result tells you only that a monotonic function is continuous almost everywhere. The next result, which is usually called Lebesgue theorem, tells you that a monotonic function is in fact differentiable almost everywhere. I will just state that theorem. Theorem, usually called Lebesgue theorem. Lebesgue differentiation theorem, some people call. Let f from AB to R be a monotonic function. Then f is differentiable almost everywhere. It's not only continuous, which you know from real analysis, it is in fact differentiable almost everywhere on AB. I shall skip the proof. The proof is too technical, lengthy, and I have to introduce so many things if I want to prove this, like Vitali's covering lemma, 4 types of derivatives, which is usually called Denis derivative, etc., etc. That itself will take 2 hours. So let us accept this result. Those who are interested to learn the proof, please consult any standard book on measure theory. For instance, the book that I have suggested from the beginning, the measure theory by Bartley, or maybe Royden, whatever you want, or Debara, measure theory by Debara. Any standard books will contain a proof of this. So proof is skipped. Too much lengthy and too much technical. But it is a very innocent statement. Every monotonic function is differentiable almost everywhere. Okay, so we shall use this in proving our main theorem, namely fundamental theorem of calculus for the Lebesgue integral. Okay. So next material that we need towards the fundamental theorem of calculus is another class of function. First, I introduced bounded variation function, studied some properties. Next, I introduced this theorem without proof. And next thing that I want is one more class of function. So let me define it. Definition. You can think of this class as a more stringent version or a generalization or a strengthening of uniform continuity. You know continuous function, you know uniform continuous function. Next, I am going to define so-called absolutely continuous function. And absolutely continuous function is going to be much more stronger than uniform continuous. So you will have continuity weaker, then slightly more stronger is uniform continuity. And now in that line, we have one more, which is strongest, namely absolute continuity. Absolute continuity will imply uniform continuity, and uniform continuity will imply continuity. Okay. So having said that, let me define what is absolute continuous means. Okay. You please remind yourself about uniform continuity. Corresponding to every epsilon, there exists a delta and so on. Okay. The statement will go, the definition will go almost the same. a function g from AB to K can be either real or complex, is called absolutely continuous. Probably this notion is not introduced in basic real analysis course because the main role played by absolute continuous function is in Lebesgue integration. Okay, so because of that, mostly in real analysis course, absolute continuous function may not be introduced. On AB, I repeat, absolute continuous functions plays a vital role in Lebesgue theory of integration. On AB, if for every epsilon greater than 0, there exists delta greater than 0, like uniform continuity, such that now you have AB. What should happen is, suppose you have inside AB non-overlapping subintervals. Let us say A1, B1, A2, B2, like this. A finite family of non-overlapping subintervals. A1, B1, A2, B2, etc. A and B, open intervals. Okay. Such that, let me now write, for any finite collection of mutually disjoint subintervals I subscript I equal to AI BI. They are all subintervals. Small I from 1 to etc. up to some n. It should be finite. Okay. For any finite collection of mutually disjoint subintervals II of interval AB, summation Bi minus AI, I is equal to 1 to n less than delta implies summation I is equal to 1 to n modulus of G of Bi minus G of AI is less than epsilon. So this is the definition of absolute continuity. Given epsilon, you can find a delta such that for any collection of subintervals inside AB having total length less than delta, you have summation I is equal to 1 to n modulus of G of Bi minus G of AI is less than epsilon. Okay, so this is the definition. Now, once you understood this definition, you should be able to answer my next question, namely, do you see that absolute continuity implies uniform continuity? It's very simple. Suppose you have this. Do you see that it will be uniformly continuous?
Yes, sir.
Take n equal to 1. Take n equal to 1. And suppose you consider your A1, B1 to be AB. Then B minus A less than delta implies GB minus GA modulus is less than epsilon. What is that? What is that? Do you see that it is uniform continuity? So I will not explain much. Note. Absolute continuity from the very definition implies uniform continuity. And already you know from analysis, real analysis, that uniform continuity implies continuity. And in fact, if you are working with a closed interval AB, There is no distinction between uniform continuity and continuity. Yes. Okay. So why we are interested in absolute continuity? What is the connection between Lebesgue integration and absolute continuity? So that's the next question. So eventually we shall prove the following. We shall prove that the following. And once we prove this, you will realize the connection between Lebesgue integration and absolutely continuous function. Okay. If what we want to prove next is the following. F is in L1AB. I hope I have introduced this notation L1AB. What does it means? What does it mean? Did I introduce this notation L1AB? Collection of all functions
Yes,
defined on AB, which are Lebesgue integrable. That is integral mod of dm is finite. Okay. So let f is in L1AB, and since f is in L1, you can talk about Lebesgue integration of f over the interval AB or over any subinterval inside AB. Okay. And let me consider capital F of x is equal to integral f dm. It is Lebesgue integral, but still I will write a to x for every a less than or equal to x less than or equal to b. I think I have named this. This is called indefinite integral. Okay. So given a Lebesgue integrable function, you can think about an indefinite integral, which is again a function of x. And the theorem says that then this new function capital F is absolutely continuous. Is absolutely continuous. We shall prove this theorem. Not now. Okay. So this will tell you what is the connection between Lebesgue integral, Lebesgue integrability, etc. with absolute continuous. If you have a Lebesgue integrable function, its indefinite integral is going to be absolutely continuous. Okay. Indefinite integral of a Lebesgue integrable function is absolutely continuous. So that is the tagline. You should keep this in mind. Okay, that's our next theorem, main theorem. Is that okay? So we have introduced a new class of function, absolutely continuous. Why we want absolute continuous while studying Lebesgue integration is because of this result. In fact, we will prove something more later. Okay, if you have a Lebesgue integrable function, its indefinite integral is an absolutely continuous function. This is one way to generate absolute continuous function. Take a Lebesgue integrable function and integrate, you will get an absolutely continuous function. So this gives you a rich source of absolute continuous functions. Okay. Now, later, after proving this result, we shall in fact prove that these are the only possible ways in which absolute continuous function comes. In other words, if a function is absolutely continuous, you can write it as integral of an L1 function. Are you getting me?
Yes, sir.
If you have an L1 function, Lebesgue integrable function, its indefinite integral is absolutely continuous. We are yet to prove it. And after proving this, we shall prove that, in fact, this is the only way to get absolute continuous function. Namely, any absolute continuous function can be identified as integral of an L1 function, integral of a Lebesgue integrable function. Okay. So that is next stage. Now, first we want to prove this, and again we have to collect some material for this. We cannot prove it as such right now. Let us prepare ourselves for this result. Okay. So again, let us go back. I have introduced a new class, namely absolutely continuous function. I have not given you any example because later I am going to prove a result which will give you rich source of constructing absolutely continuous function. Start with any L1 function, integrate it from a to x, you will get an absolutely continuous function. And I have given enough non-examples. Once you have non-uniformly continuous functions which are not uniformly continuous function, they cannot be absolutely continuous function. So non-examples are given. Examples I am not giving now, but I will give you a result to generate more and more examples, namely this result. Okay. So far so good. Okay. So what's our next aim? Forget about fundamental theorem of calculus for the time being. Intermediate, we have our next aim, namely to prove that given an L1 function, its indefinite integral is absolutely continuous. Okay, so let us prepare ourselves for this. Let us set the stage for this. And towards that, I am going to state and prove a consequence of DCT, dominated convergence theorem. Okay. Theorem. A consequence of, it's a corollary actually. I could have done there, but I forgot. A consequence of dominated convergence theorem. All these things will give you material needed to prove this result. A indefinite integral of an L1 function is absolutely continuous. Okay, so having said that, now without much delay, let me state the theorem. What is the consequence of DCT that I am talking about? Let f is in L1. F is a Lebesgue integrable function. Okay, or maybe f is in, if you want slightly more general, L1E, where E subset of AB is measurable. Okay, f is a function from, let me start like this. Let f is a function from AB to K, where K is either R or C. So real or a complex valued function defined on AB. Assume that f is Lebesgue integrable on AB, or you can assume it is Lebesgue integrable over E, where E is a subset of AB. Okay. Now what the theorem says is the following. Let Fn of x, I'm going to define a sequence of function. F of x, Fn of x will be f of x if modulus of f of x is less than or equal to n, and it is n if modulus of f of x is greater than n. It's actually a truncation of f. Then for each n, Fn is bounded, Fn is measurable, and integral over mod Fn minus f dm. E or AB, depending upon how you are taking the, okay. So I'm not writing integral over what, tends to 0 as n tending to infinity. So basically it tells you that roughly any Lebesgue integrable function you can approximate via a bounded measurable function. Approximation in the sense that integral of mod Fn minus f dm tends to 0. And you can see that once integral of mod Fn minus f dm tends to 0, this is the third part of the dominated convergence theorem, which I wrote as a consequence or a remark. From this, you can prove that integral Fn dm converges to integral f dm. That's not hard. That is the conclusion we wrote as DCT is actually a particular case of this. integral mod fn minus f dm tends to 0 will automatically give integral fn dm converges to integral f dm. Are you with me?
Yes, sir.
Yes, sir.
That how does it follow? That follows from the fact that modulus of integral is less than or equal to integral of the modulus. Modulus of integral over E f is less than or equal to integral over E mod f. Using that, once you have integral mod fn minus f dm tends to 0, automatically you will have integral fn dm converges to integral f dm. So this is more powerful consequence of DCT. I mean, the last statement. Okay. Anyway, so in that sense, what the theorem says is that once you have a Lebesgue integrable function, then you can approximate it via a bounded functions. Okay, boundedness is important. Now let us prove this result. It is just 1 or 2 lines. It is based on dominated convergence theorem, as I told already. Okay. Now, if you watch Fn, closely watch Fn, what we are doing is this. You are given with a function f of x. Okay. So let this be the Cartesian plane and you have a function f of x. Okay. And fix this interval minus n. Okay. If your functions lies between minus n and n, take fnx as it is. And once it crosses minus n, you just put your fnx as n. If it crosses n, you take it as n. Okay. N or minus n, then you take it as n. So this is how you are constructing your fnx. Okay. So in fact, you can see that fn is this notation is usually used for minimum. That is minimum of mod fn, mod f n. The function sequence of function fn is defined like this. Take minimum of the function mod f and n. Okay, this is how you have defined your fn. It is same as saying fnx is f of x when mod f of x is less than or equal to n, and it is n if mod f of x is greater than n. Okay. Now let us prove that result. What is to be proved? Each fn is bounded, measurable, and then integral over this. To prove the last part, I shall invoke dominated convergence theorem. Okay. For that, first you want domination. That is, each fn should be dominated by an integrable function. Okay. Now, note that. So let us start the proof. Note that modulus of fn is less than or equal to n. Do you agree? For that only I wrote it as minimum
Yes, sir.
of. Once you identify it as minimum of mod of n, it is easy. Similarly, modulus of fn is less than or equal to mod f for all n. By the very definition, this follows. Okay. Now I claim that fn converges to f pointwise. So you were given with the f, you constructed a sequence of functions fn, and we claim that the sequence of function that you constructed converges to given function f pointwise. Okay, that's quite straightforward. What is given? F is a function from a, b to k. Therefore, f is complex value, real or complex value. So since I'm going to establish this claim, okay? Since f is complex valued, for each x in AB, mod f of x will be a real or complex value. So modulus of f of x is going to be a real number, finite real number, okay? for every x element of AB, modulus of f of x. I'm not talking about extended real valued function. F is a function from AB to K. K is either R or C. So modulus of f of x is going to be a finite real number. And given any real number, there exists a natural number greater than it. Therefore, I can find, since f is complex valued, for every x element of AB, there exists a natural number k such that modulus of f of x is less than or equal to k. Do you agree? Do you agree?
Yes. Yes.
Because mod f of x is a real number and you can always find a natural number greater than it. So your fx graph you remember. So suppose this is k and this is minus k. Okay. If n is greater than or equal to k, so that for n greater than or equal to k, fn of x. Can you tell me what will be fn of x? Remember the definition of fn of x. Fn of x is f of x if mod f of x is less than or equal to n, and it is n if mod f of x is greater than n. Okay. And I am fixing n to be greater than or equal to k. And I know that mod f of x is less than or equal to k. So do you see that fn of x will be equal to f of x? No?
Yes, sir.
Mod of f of x is less than or equal to k. Keep that in mind. Okay. And what is fkx then? Remember what is fks? See the definition of fkx. Okay. Therefore, for n greater than or equal to k, I will have fnx is equal to f of x. Okay. That's not hard to see. Now, do you see that mod fn is dominated by an integrable function? Mod fn is less than or equal to mod f, and f is in L1. F is in L1. Therefore, mod f is integrable. So mod fn is each of the function in this sequence is dominated by an integrable function, and fn converges to f pointwise. So this is a perfect place to apply
Dominated convergence theorem.
convergence theorem. Therefore, by dominated convergence theorem, by DCT, integral mod fn minus f dm tends to 0. This outcome of DCT I have not written as a part of DCT, but I wrote it as a remark, if I remember correctly, as n tending to infinity. And further, this output of DCT will automatically give the other things. Integral fn dm converges to integral f dm. Okay. So this is one result what we want as a preparation towards the result aimed at, namely the integral of an L1 function is absolutely continuous. Okay, that we want to prove, and for that we stated and proved one consequence of DCT. Okay, now we want another result as a preparatory material, and to motivate that result, let me make a remark. Okay. So this finishes that theorem remark. This remark will motivate the next theorem that I am going to state and prove. Please recall that if you have an integrable function, or forget about integrable, measurable function, and you are integrating over a set of measure 0, then what can you say about the integral value? You are integrating a measurable function over a set whose measure is 0. Then what can you say about the integral value?
0.
0.
Okay. Recall that if f is a, I might have not proved it in general, I might have proved for non-negative and so on, but then you can extend it. Okay. For step function, it is clear. And then you can prove for non-negative function. and then you can prove for general function. If f is a measurable function, and E subset of R is measurable, with the measure of E equal to 0, then integral over E mod f dm will be equal to 0. Try to prove it, if at all I have not proved it. Okay. But now, suppose measure of E is not 0, but measure of E is very small. Okay. Then what is the natural expectation? If measure of E is 0, integral of mod f dm is 0. Okay. That I have proved at least for non-negative functions. Okay. Now, with this in hand, if measure of E is not 0 but small, what do you expect for the integral value? Intuitive expectation. If measure of E is 0, integral becomes 0. Therefore, if measure of E is small, what do you expect for the integral?
Small.
Small, right? Suppose measure of E is not 0, but it is small. Can we expect integral over E mod f dm is also small? Okay. Let me give you a quick example to answer this. Example. Let me consider f from R to R. Okay. Where f of x is defined like this. 1 by x square when x is non-zero and 0 otherwise. That means x is equal to 0, f of x is defined as 0. Okay. So now let me see what happens to integral when the measure of a set is small. Okay, first I have to construct a set of small measure. Consider, look at this. An is equal to collection of all x in R such that 0 less than x less than 1 by n. In fact, it is an interval. Okay. Then what is measure of An? I have written in this way, but it is actually the interval 0, 1 by n. What is measure of An?
1 by n.
1 by n. It is an interval, so measure is length. Okay. So if n is large, measure is small. Measure of each An is small. Now let me consider integral over An mod f dm. Okay. So measure of An is small. Now let us look at integral over An of this function, mod f dm. By definition, integral over An is integral over R chi An mod f dm. This is the definition of integral over An. Okay. Now, on An, x is less than 1 by n. And therefore, 1 by x square is greater than n square. Agree? X is less than 1 by n. Therefore, 1 by x square is greater than n square. Yes or no?
Yes.
Therefore, this is greater than or equal to, remember mod f is a positive function, non-negative function. And mod f is greater than or equal to n square. Therefore, integral over mod f will be greater than or equal to integral over n square, chi An dm. Now, n square is a constant. It doesn't depend on x. Then integral over chi An dn. Chi An is a simple function. So, integral is measure. So, measure of An. And measure of An is 1 by n, and this is n. Okay. So what happens to integral when n become large? Is it small? When n becomes large, measure of An is small, but integral over An mod of dm is not small. Do you agree?
Yes, sir.
Thus, measure of an tends to 0 in fact, as n tending to infinity. This is just a simple example, but integral over an mod f dm tends to plus infinity. So if measure of a set is 0, integral over that set will become 0. From that, roughly, you may expect that if measure of a set is small, integral will be small. That is not right. That we have seen through an example. Now, in the next theorem, what I am going to prove is such an unpleasant situation will not happen if your f is an L1 function, if f is an integrable function. Okay. So with that background, let me state the theorem. Again, this is not the main theorem. This is just a preparation towards our main theorem. Okay. The statement is like this. Let f is L1. F is in L1. Okay. Then f is a Lebesgue integrable function. Then for each epsilon greater than 0, there exists delta greater than 0 such that a subset of R, a measurable, is a measurable set. Measure of A is less than delta implies integral over A mod of dm is less than epsilon. Roughly, when measure of a set is small, integral over that set is also small, provided the function that you are integrating is an integrable function. F is in L1. Okay. So you can make the integral to be as small as you want by taking measure of the set to be small enough. So this is progress towards the example. Example tells that it may not be possible. When measure of a set is small, then integral may not be small. Why this happened? Because the function that we took there is not a Lebesgue integrable function. Okay, you please check it. But once you start with a Lebesgue integrable function and measure of a set is small, integral over that set also will be small. Is that okay?
Yes.
Now let us prove it. Okay. So I will prove it in two steps. Given function is only in L1. Nothing is told about its boundedness. First, I will assume f is bounded and I will prove the result. And in the second step, I will go for a general function which may not be bounded. Okay. Let epsilon greater than 0 be given. I have to produce a delta having this property. Measure is less than delta implies integral is less than epsilon. Let us assume that f is bounded. Assume f is bounded. This is an additional assumption not given in hypothesis. Say modulus of f is less than or equal to some constant m naught. Okay, so I have to find integral over a mod of dm. Okay. Then integral over a is some set which is measurable, mod of dm. Mod f is less than or equal to m naught. Therefore, integral over a mod of dm is m naught times measure of a. Do you agree?
Yes, sir.
What I want is integral to be less than epsilon. Okay. What delta I should choose? If I want integral to be less than epsilon, I need to have only m naught times m of a is less than epsilon. That means I have to choose m of a to be less than epsilon by m naught. Yes or no? So if measure of a is less than epsilon by m naught, call it delta, then integral over a mod f dm would be less than epsilon. M naught times epsilon by m naught. So we are done. Okay. Given any epsilon, choose delta to be epsilon by m naught. I will get whatever is needed. Ma less than delta implies integral over a mod of dm is less than epsilon. So things are fairly straightforward if the function is bounded. Now, next consider non-trivial case. Next consider the general function. A general function f in L1. I don't know whether it is bounded or not. F in L1. Okay. Now, given any function f in L1, I can approximate it by a bounded function. Previous lemma. Not lemma, theorem. This one. Given an f in L1, I can find a sequence fn such that integral mod fn minus f dm tends to 0. I am going to use that. Okay. By the previous theorem, so first I proved for bounded. Now I will make use of the previous theorem, namely any integrable function I can approximate it by a bounded function. By the previous theorem, there exists a bounded function g. In fact, the previous theorem says that there exists a sequence of bounded function, but from that I can get a bounded function g such that integral mod f minus g dm is less than epsilon by 2. Do you agree? Do you agree? Are you people there?
Yes, sir.
Is that clear? You can construct a sequence such that integral mod fn minus f dm tends to 0. Once you have a sequence, I can get one function g such that integral is less than epsilon by 2. Now, therefore, integral over a mod of dm. This is what we want to make less than epsilon. Is now apply triangle inequality and so on. Integral over a mod g dm plus integral over a mod f minus g dm. Introduce g. In place of mod f, write mod f minus g plus g. Then apply triangle inequality like thing, you will get this. This is less than or equal to integral over a mod g dm plus second quantity is less than epsilon by 2. No issue with that. Now, how to tackle the first term in the right hand side? Remember, g is bounded. Okay. Since g is bounded, there exists some m such that modulus of g is less than or equal to m. Okay. Therefore, integral over e mod f dm is less than or equal to mod g integral will be less than or equal to integral of m. M is a constant and then measure of a will come. That will be the integral of m plus epsilon by 2. Okay. Now I want to make integral of over e mod of dm to be less than epsilon. Okay. What is enough? Thus, if we choose delta is equal to epsilon by 2m, we get measure of a less than delta implies not integral over e, it should be integral over a here. Integral over a mod of dm is less than, first quantity will become m times epsilon by 2m. Therefore, it will be epsilon by 2 plus epsilon by 2, which is less than epsilon. So given epsilon, I could find a delta such that measure of a less than delta implies integral is less than epsilon. Okay, is that okay? So we proved the result. Yes or no? Do you agree?
Yes, sir.
Now, give me 5 minutes because otherwise I have to recall all these things in the next class again. With all these preparations, we can prove our intended result. What was intended? The intended result was what is the connection between absolute continuity and Lebesgue integration? If f is in L1, then the indefinite integral is absolute continuous. That was the result I promised. Now we are ready to prove that theorem. Give me 5 minutes. And the proof is very simple now with all these preparations. Let f is in L1 AB. F is an integrable function on AB. And define capital F from AB to K by capital F of x is equal to integral a to x f df for every x in AB. So it is indefinite integral of a Lebesgue integrable function. Then capital F is absolutely continuous. Capital F is absolutely continuous. Okay. That is indefinite integral. This is the statement actually. Indefinite integral of a Lebesgue integrable function is absolutely continuous. What do you know about the integral of a Riemann integrable function? Suppose small f is Riemann integrable, integral a to x small f dx is do you remember?
Continuous.
Continuous. So integral of a Riemann integrable function is continuous. Here you have something more. It is absolutely continuous. Okay. Proof. But remember, once it is Riemann integrable, it is Lebesgue integrable, and once it is Lebesgue integrable, we have absolute continuous. So we have something stronger than what you proved in Lebesgue integration. Okay. So now let me prove it. Proof is very simple. To prove absolute continuous, what should I do? Given epsilon, I have to find a delta such that that overlapping subinterval I have to. So let me start with overlapping subintervals, non-overlapping. Let AI, BI I is equal to 1, 2, 3, etc. up to n be a family of non-overlapping subintervals. Just recall the definition of absolute continuity of AB. Okay. Now let me try to find. I have to estimate summation I is equal to 1 to n modulus of f of ai minus f of bi. This I want to make less than epsilon by taking summation bi minus ai less than delta. That is the definition required. This is equal to summation I is equal to 1 to n. This is integral. Oh, sorry. Capital F. No, because I want capital F to be absolute continuous. Capital F, capital. I am checking absolute continuity of the capital F function. But now capital F is integral a to ai small f. Okay. So apply that, you will get this as integral ai to bi small f df. Okay. This is less than or equal to, this is just calculation. So I will keep on writing integral ai to bi mod f df. Here I have used the fact that modulus of the integral is less than or equal to integral of the modulus. This I will write as integral over a mod f df. Can you guess what is a? Where a is, who can tell me what is a? Is this so hard? Summation integral over AI, BI, I want to identify as integral over a set A. What is that set then?
A comma B.
No, because AI, BI may not cover entire AB. Here you have AB and this is your A1, B1 maybe. This is your A2, B2. There may be something missing in the absolute continuous definition. It may not be entire AB, okay? So A is union I is equal to 1 to N AI, BI. Do you agree?
Yes, sir.
Now what is measure of A? Now, measure of A. Remember, AA, BAs are non-overlapping. There is no intersection. So what is measure of A? Summation I is equal to 1 to N BI minus AA. Yes or no?
Yes, sir.
Now use the previous theorem. If measure of A is small, integral over A mod of dm is small. Right? By the previous theorem, measure of A less than delta. For every epsilon, there exists a delta such that measure of A less than delta. For every epsilon greater than 0, there exists a delta such that measure of A less than delta implies measure integral over A mod of dm is less than epsilon. This we know. Okay, that is, what is the meaning of measure of A less than delta? Summation I is equal to 1 to N BI minus AI is less than delta implies, okay, once integral over A mod of dm is less than epsilon, summation I is equal to 1 to N mod fi minus fba is also less than epsilon. Summation I is equal to 1 to N modulus of capital F of AI minus capital F of BI is less than epsilon. Now what is this? What is this? Given epsilon, there exists a delta such that whenever you have a non-overlapping subintervals whose sum of length is less than delta, summation f of AA minus f of BA is less than epsilon. What this tells you?
F is absolute continuous.
Therefore, capital F is absolutely continuous. Quite easily done. So, integral of a Lebesgue integrable function, indefinite integral of a Lebesgue integrable function is absolutely continuous. In particular, it is continuous. So, we will stop here. And fundamental theorem of calculus is in fact the converse of this. That is, any Lebesgue integrable function you take, it will be of the form, any absolutely continuous function you take, it will be of the form integral of an L1 function. I repeat, now you proved that if you start with an L1 function and you integrate, you will get an absolutely continuous function. And we are going to prove the converse. Okay, start with any absolutely continuous function. You can write it as integral of an L1 function. Is that clear? That is going to be one part of fundamental theorem of calculus. Start with any absolutely continuous function, then that can be identified as integral of an L1 function. That is going to be one part of fundamental theorem of calculus. I wanted to complete it today, but anyway, so 1 more hour we may have to spend for fundamental theorem of calculus. It's okay. We are going too slow, I think. Let me stop here.